Now we are going to talk about things you certainly learned before. You've seen them in the probability course, and you've seen them in many courses you joined before starting this master's program. And the first question I would like to consider is the definition of random variable. In my practice, only about 1 in 200 students remembers what is a random variable when they join this course. And have a think about it for a second. Now, the proper definition of a random variable is that it is a function, and it is a function that maps the sample space, possible outcomes of a random experiment, onto some set of values, usually numbers, sometimes categorical variables, but we will consider as general numbers. And, first of all, the random variables are not direct outcomes of a random experiment. Say, when you are rolling a die, you are not seeing numbers, you are seeing pictures which is on the top side of the die. So you will see one of the 6 possible pictures. And a random variable is introduced when you map those pictures onto numbers. So the random variable is actually the function which introduces this mapping. Random variables can be discrete, can be continuous. So discrete random variables are those that have countable number of outcomes in the image of the function. So if we roll the die, say 10 times, and take note of the side facing upwards, we can define a random variable as the sum of all 10 outcomes. In that case, the random variable will map these possible outcomes onto numbers from 10 to 60. And because numbers 10, 11, 12, 60 can be counted, there are only 51 of them altogether, that means that the random variable is a discrete random variable. Another type of random variables is continuous random variables, and they happen when the values that random variables take are not countable. Say, the weight of a light heavyweight professional boxer is defined as weight between 168 and 175 pounds, which means any value, something like 169.321, is still a possible value, and you cannot count all possible numbers within the interval of real numbers. That means it is an uncountable set, and that means that our random variable is continuous. Once you define a random variable, that implies that you have some distribution over possible values of that variable. That means probability is spread somehow between possible values that random variable takes. And that spread of probability is defined for discrete variables with probability mass function, for continuous variables with probability density function, and for both of them there exists cumulative distribution function. And you can see the definitions of these in the lecture notes, and you will see several examples of different distributions. When you consider several random variables at the same time, they may depend on each other, and therefore we will have their joint probability distribution. And that joint probability distribution is describing how the values depend on each other of different variables. Consider this example. We will study the passengers on Titanic when it sank. And we will consider that the passengers were in 4 different categories. There were passengers who traveled in the first class, there were passengers who traveled in the second class, and there were also passengers who traveled in the third class, and there were crew. Some of people survived sinking of Titanic, some of people unfortunately died. Therefore, we can classify all the passengers into 8 possible combinations, whether they were survivors or whether they unfortunately died, whether they were in the first class, whether they were members of crew, whether they were in the second class, and so on. So, to study this problem, we will introduce 2 discrete random variables. The first one, the variable x, will be 0 if the passenger was survivor, or 1 whether the passenger died in sinking of Titanic. Variable y will define whether the passenger was in the first class, and that value will be 1. In the second class, taking value 2, third class, taking value 3, or they were members of crew, taking value 4. Both x and y are discrete random variables. Now, we can define the joint probability mass function in this case. And for any value, for example, x equals 0, y equals 1, we can define what is the joint probability of that particular case, being in the first class, y equals 1, and surviving sinking of Titanic, x equals 0. And in that case, the probability will be about 9%. Imagine we are looking for the probability of surviving regardless of the passenger class. What is the probability of surviving while being on Titanic? In that case, we have to consider the marginal probability of one of the variables. That means we are looking for probability of survival, probability of x equals 0, regardless of what was the value of y. That's why we will take all the joint probabilities for y equals 1, 2, 3, 4, and we will add them together to get the marginal probability for survival in this case. And that would be about 32%. So about a third of people survived sinking of Titanic. Finally, we need to consider the conditional probability. Imagine we want to find out what is the probability of passenger being a survivor given that they were traveling in first class. And for calculating that, we will condition value of x on having observed value of y to be exactly 1. So y is no longer a random variable, it is fixed. We know that y is 1. What is now the probability of x? And for that, we will take probability of x equals 0, y equals 1, the joint probability, and divide it by the marginal probability of y equals 1. And in this case, that will be probability of 9% divided by probability of 14% for the marginal probability of being in the first class. And that will give us that if you were lucky enough to travel in the first class, your probability of survival would be 63%. Joint probability also exists for continuous random variables. And let's consider a simple example. When we have two variables and they somehow depend on each other, their joint probability is the density of different combinations of x and y. And here is the surface plot for that density. Sometimes it is easier to talk about that looking at the contour plot. If you are not familiar what the contour plot is, open a Wikipedia page called Contour Lines, and that will explain exactly how to read this plot. Some people prefer to use heat maps, so brighter red color would mean higher probability and the yellow colors mean lower probabilities. I will prefer using the contour lines in this case. So this describes that values around x equals 0, y equals 0 are most likely. Values outside of that point, farther away you get, are less likely, and there is some dependency between x and y because this whole joint probability is tilted somewhat. Let's talk about marginal probabilities first. Consider we want to see what is the probability of y regardless of what the value of x is. What we have to do in this case is to go along these horizontal lines and add all the probabilities up to get a value over here for the value of marginal probability of y. The case is that we have continuous variables, so we cannot add values up, and the sum will simply be replaced by an integral in this case, and we will get the value of the marginal probability at that point. Then we will continue looking at different points here, and we will add numbers up along these lines, and we will get corresponding values of the marginal probability. We can do exactly the same for the other variable. We can consider marginal probability of x regardless of the value of y. In that case, we will go along vertical lines here, and we will integrate along those lines to get the values of the marginal probability for x. Lastly, we need to consider the conditional probability. So imagine we know the value of x, and it is here emphasized with a dashed line. Now, the distribution of y, given that we know that x is there, is obtained by just slicing through this hill, slicing through this joint probability, and considering what is the profile of that hill along the line. And that would be this dashed plot over here. So, formally, marginalization is performed the following way. We take the marginal probability density of x, and that is obtained by taking joint probability of x and y and integrating out y. Evaluating this integral will provide us with the marginal probability. Conditional probability can be obtained by taking the joint probability of x and y and dividing it by marginal probability of y. Rearranging terms in this expression leads us to an interesting property for factorization, and we will use this property several times in the course. When we have, say, marginal probabilities, we have conditional probabilities, and we want to obtain the joint probabilities. And that means that joint probability can be expressed as marginal probability multiplied by the conditional probability. It also works for vectors. In that case, we can express the joint probability of the whole vector as marginal probability of the first component multiplied by conditional probability of the second component, given that we know the first component, multiplied by the conditional probability of third component, given that we know previous two, and so on until the last component in a vector. Next topic that you probably learned before is transformations of random variables. That happens when we have some random variables, some random variable, say u, and it has some probability density function. Now we want to apply a function to the value of that u, and that will be a new random variable v, which is just a transformation which normally should be continuously differentiable. So what would be the probability density function for v? And that probability density function can be obtained by applying a reverse transformation to the value of v, substituting that into the original probability density function, and finally we have to multiply it by the absolute value of u of the derivative of u by dv. Now, this also works for vectors. The only thing that changes is that, well, v and u are vectors, but this derivative, we need to take the Jacobian matrix, which is the matrix of partial derivatives of u by v. Have a look in the lecture notes for the definition of J. Take determinant of that matrix, and finally the absolute value of the determinant will give us required correction term in evaluating the probability density function for v. I give two detailed examples of how to perform variable transformations in case of just single random variable and in case of a vector of random variables in the lecture notes. Please read those examples. Next thing you certainly seen before is Bayes' theorem, and surprisingly Bayesian statistics takes the name from Bayes' theorem. This theorem describes how to swap variables around the conditioning sign. So if we have a conditional distribution of b given the value of a, and we want to find the conditional distribution of a given the value of b, we should apply this expression to evaluate the corresponding conditional distribution. Let's see how that happens on an example. Consider we are evaluating a clinical test for certain disease. So you go to a doctor, they draw your blood, and they perform a test whether you have some disease or not. So we are interested to find out that if the test is positive, what is the probability that you actually have the disease? Because sometimes tests fail, and it's not guaranteed that if the test is positive, you actually have the disease. So let's consider this scene and set up all the random variables required for analysis. So I will introduce two random variables. The first one will be a discrete random variable d. variable d will take value 0 if you don't have the disease. Variable d will take value 1 if you do have the disease. I will also introduce variable t for test. If the test is negative, variable t will be 0. If the test is positive, variable t will be 1. Now, as we analyze the clinical test, we have to know certain properties of that test. The first one is the rate of false positives. So, what is the probability that you don't have a disease, but the test will come back as positive test? And we will say that some probability alpha corresponds to that. The next one is probability of false negatives. Say you have the disease, but the test says you don't. And that probability will be beta. Next, obviously, the probability of true positive is 1 minus beta, and the probability of true negative is 1 minus alpha, because probabilities have to adapt to 1. Finally, we need to know how prevalent the disease is in the population. So if you take all the people on Earth and see how many of them have the disease, that will give you the probability of having the disease in general. And obviously, the probability of not having the disease is 1 minus gamma. Now, applying Bayes' theorem will allow us to compute the probability of actually having the disease given that you tested positive. And that probability will be a fraction here. And in the numerator, we will have probability of test is 1 given that disease is 1. Here I switched t and d around in comparison to what we are looking for, multiplied by probability of having the disease in general population. And we need to divide this whole thing by the probability of test equals 1 given the disease equals 1 multiplied by the probability of the disease in the population, just the same thing as in the numerator, plus the other option, testing positive when you don't have the disease. So probability of test equals 1 given that disease equals 0 multiplied by the probability that disease equals 0 in the population. Now we can take our alphas, betas, gammas, substitute them here and compute the actual probability that we're looking for. Let's consider a particular case. Say the false positive rate is 1 out of 20. So if you don't have the disease, with probability of about 5%, you will get a false positive result of the test. False negative will be 10%. So you have the disease, but the test says you don't. And say the disease is about 1 person in 1,000 has it. In this case, the probability of having the disease given that you tested positive will be 1 minus beta, that is the probability of testing positive given that you have the disease, multiplied by gamma, and that is the probability of having the disease in general, divided by the same thing plus probability of the false positive given that you don't have the disease. And in that case, you will see that even though you tested positive, the probability of actually having the disease is less than 2%, which means it is probably not a very good clinical test. Next topic I want to cover is the idea of using simulation for evaluation of difficult things. Quite frequently, we will be working with multidimensional problems. So we will be working with random vectors. And say one of the problems we will consider is evaluation of the marginal probability density of one of the components of that vector. And for that, we will need to integrate all the other components out. The problem with this integral is that frequently in practice it is infeasible. So if you start evaluating this integral analytically, you will never get a closed form solution. If you start evaluating it numerically with, say, some kind of a trapezoidal integration method or something like that, what happens is that you need to introduce a fine grid over zeta 1, fine grid over zeta I minus 1. Over every zeta, you need to introduce some fine grid for trapezoidal integration, and that results in enormous computational effort to evaluate that integral. It is not feasible in practice. We will consider some idea which will rely on sampling to evaluate these things, and that will be much easier than any attempt at evaluating the integral directly. So imagine we can draw values of the random vector from the distribution, and we will have a sample, and we will put it in the table. Rows in the table will be different samples. So one attempt, second attempt, third attempt, attempt number capital L. The columns will be different components, so zeta 1, zeta 2, and so on up to zeta k. Now, if we wanted to find out the marginal distribution of zeta 2, for example, we will just take this column, and that would be a sample from the corresponding marginal distribution. What can we do with that sample? Well, first idea is to use something called kernel density estimation to get an approximation to the probability density function based on a sample. Consider a simple example. We have values 1, 1.5, 1 3/4, 2 and 3, just drawn from some random distribution. 5 values is our sample, and we want to estimate approximately what is the probability density of that random variable. The idea of kernel density estimation is to put a Gaussian on top of every value of the sample. So I will put a Gaussian with mean at the first value here, and I will choose the variance of this Gaussian somehow. This is called the bandwidth. And I can change different values, I can try different values and see which values give me the most desirable results. So I will put such a Gaussian on every value. On the first one, 1, at 1.5, at 1 3/4, at 2 and at 3. So I have these 5 Gaussians, and then what I do, I go through the whole range of values and I average out all 5 of them, which will be the density of the first one multiplied by 1/5 plus the density of the second one multiplied by 1/5 and so on. And this would be the result. And this result, the white line, is actually an approximation to the probability density function for that sample. By changing the variance of these Gaussians, I can tune the smoothing of this white line. So if I was choosing wider Gaussians like this, my outcome, the estimate, will be smoother. And obviously you don't need to do it manually. Most software packages support kernel density estimation in them. For example, in R, I may want to estimate the gamma density, and for that I just use the function density, and this performs kernel density estimation. So in these two lines, what do I have? I draw 1000 realizations of a gamma distributed random variable with parameters shape 2 and scale 2. Now, by running the density, that takes every one of 1000 values in X, puts a Gaussian on top of them, estimates what kind of variance that Gaussian needs, and averages them out and produces the result in this variable d that I can then plot. So over here what I have is the actual density. This is not estimated from the sample, this is just direct gamma density with parameters 2, 2. And on top of that, in purple line, I will draw our density estimate using kernel density estimation. You can see it is an approximation, it is not exact, but it follows the green line quite closely. And the secret is, as you increase the number of samples here, the lines will get closer together. So if I took, instead of 1000 samples, if I took 10,000 samples, the lines will be closer together, and so on. This doesn't happen only in one dimension. You can do the same with multidimensional distributions. Say we have a joint distribution of two variables here, and those dots on a plot are a sample from that joint distribution. Now in the package, in our package mass, we have a function called KDE2D, which is kernel density estimation for 2 dimensions. And I will take values of the first variable and values of the second variable. And this function will put a bivariate Gaussian on top of every dot in this plot and estimate the smoothed out version of the kernel density estimation. I will end up with kind of this shape. This is a heat map of the resulting estimated joint density. And if I overlay my dots, I can see that actually the density matches what I observe in the sample quite well. Finally, having that sample, you can evaluate just simple statistics from that sample. If you are interested to find out what is the mean of the random variable based on the sample, you just take the mean of that sample, the average of that sample, and that will be a good estimate for the mean of the random variable. Similarly, you can do median, and you can estimate, say, 95% percentile, 95% confidence interval about the value of that random variable. It all can be done based on the samples from that variable stored in a vector in this case. Transformations. If you read the part in lecture notes about performing transformations properly with evaluating the derivative and so on, you found that it was quite difficult, and you would imagine that the more difficult your distributions are, the problem will be more and more challenging. This can be easily done on a sample. The first example in the lecture notes, we are taking a standard normal variable u, and we are evaluating the distribution of u squared, which we call v. And it is kind of several lines, several steps in that proof to find out what is the distribution of that v. What I do here, I just take the sample from standard normal variable u. I take actually 10,000 samples, and I square every single one of them, and I put that into variable v. I just apply that transformation directly to the values of the sample. And then I use kernel density estimation to see what is the distribution of resultant v. Here is the plot. The purple line is actually that function that is evaluated in the example in the lecture notes. This is the exact solution. And I will put on top of that the white line. This is the line evaluated by just squaring every u in a sample and evaluating kernel density estimation. They match pretty closely, in my opinion, which shows that using simulations, by drawing random variables and applying operations to a sample, you can basically achieve the same results much easier than integrating properly or transforming variables properly. Finally, in the end of this chapter, you will find a number of review exercises. These are optional. I will never check whether you performed it or not. I actually provide solutions for them as well. If you want to rehash on these basic ideas, you might want to attempt those exercises and see how well you perform.